we can say that HCl is called a polar molecule. If I draw that HCl one more time right here, we had arrow towards the chlorine, partial positive, partial negative. What we can imagine is that we can separate this into a partial positive and partial negative side. Okay? If we sort of divide this, we've got a positive side over here, we've got a negative side over here. What that actually means is that in the HCl molecule, because the chlorine is pulling electrons that way, that this side of the molecule has a lot more electrons to it than this side does. Okay? This side is a lot more negative, and this side is more positive. Okay? And that has a lot of consequences for the properties of those molecules. Turns out polar molecules are attracted to each other, because if I had another HCl over here, there's its positive side, there's its negative side. Okay? The opposite sides of those molecules will attract, just like magnets. Okay? If you draw a magnet, right? Magnets have a bar magnets have a north pole and a south pole. It's only those opposite sides that are attracted to each other. Okay? So, polar molecules, here, let's do something like that. There's an attraction. So polar molecules are kind of sticky. You can think of it like that. Because if I've got a negative side and a positive side, whoops, not anymore. These are going to act just like magnets. What would happen if they tried to come at each other like that? They would repel. Okay? And in fact, this one would probably just flip over and they'd stick like that. Okay? So just think of little bar magnets. That's what polar molecules are. Okay? And that's going to have real important consequences for us later on when we talk about the properties of molecules. Because if molecules are really sticky, that changes how easily they boil and evaporate, and their surface tension, and all that sort of stuff. Okay? So polar molecules are sort of sticky like that. They're attracted because they have opposite charged ends. Okay? A net dipole moment is just one arrow that represents the polarity of that whole molecule. So depending on how we draw it, right, for this HCl above, it points from the plus side to the minus side, going in that same direction. Okay? That's going to be more important in a second when we have like multiple arrows in the molecule. Okay? But if we got just one arrow, that's a polar molecule. The net dipole moment is just pointing that same direction. Okay? It's just pointing towards in the direction of the negative side of the molecule that you've drawn. Now, a nonpolar molecule is opposite. Okay? It does not have a minus side and a plus side. Its electrons are all equally distributed, symmetrically. Okay? So we don't have a minus end and a plus end. Okay? All the electrons are just sort of all spread out evenly all around. So nonpolar molecules behave very differently. Okay? They don't behave like little magnets where they flip around and get attracted in one particular direction. Okay? That's one of the reasons why oil and water doesn't mix. We're going to see in a second, water is polar. Molecules of oils are nonpolar. So this affects lots of properties that we're going to talk a whole lot about. Okay? Coming up. So let's draw a CH3 Cl molecule, okay? And it doesn't matter where you put that chlorine, okay? As long as you have a chlorine in that molecule. Try to make a quick model here. There we go. Alrighty. So that's what CH3Cl is. like I said, it doesn't matter where you put that chlorine. We could draw this any direction we like. Okay? Doesn't matter. Okay? Where are we going to draw arrows, though, inside of this molecule? Carbon to the chlorine, right? Chlorine pulls harder than carbon because of its position on the periodic table. So draw arrow like that. Keep wanting to draw these green here. So consistent on the color scheme. Okay. What about the CH bonds? CH bonds are equal. No arrows on those. Okay. So if you think about this, this whole molecule will be affected by how electrons are being pulled inside of that bond right there. Okay? The chlorine pulls electrons that way. That makes this whole side of the molecule, right? If you sort of split it in half, this whole side of the molecule over here is more minus, right? And this whole side of the molecule over here is more plus, because that's the direction that electrons were pulled in that bond. So however you have that drawn, right, towards the chlorine, that's the minus side. Okay? And over here, that's the plus side. Now there's a little perspective depending on how you draw the H. Okay? But we can clearly see a minus side and a plus side to this molecule. Right? What does that make it? Polar or nonpolar? Polar. This is a polar molecule. I'm just going to circle that. Okay? And its net dipole moment will be pointed just in the same direction that that one arrow was pointed. Okay? So really, the behavior of this molecule, right? If we just draw this as like a big electron cloud, okay? Partial minus side over here, partial plus side over here. Okay? That's really what that means. Okay? In terms of behaviors of molecules, okay? That's really how this molecule is sort of laid out, if that makes sense. But it all comes from the pulling of electrons in that bond. Carbon pulling them away from chlorine, pulling them away from carbon in that bond right there. Okay? Now, when we do CO2, we have to be careful because it's very important that we draw this with the correct shape. We have carbon with 2 double bonds to O's. Okay? 2 atoms could either be linear or it could be bent. And what's the difference? What determines whether something is linear or bent? We could do linear like that, or we could do bent like that. 1, 2, 3, 4. 1, 2, 3, 4. Okay. Which one is CO2? Yeah. What would there have to be in order for the shape to look like this? There would have to be dots. Well, dots right there. There would have to be dots on the C. And there are not dots on C. Carbon already has 8 to it. Okay, so that's not the right shape. CO2 is linear. Okay. How would the arrows be drawn in this one? Towards, look back at a periodic table if you need to. We're comparing C and O. Which one pulls stronger? O pulls stronger. Okay? So, arrow like that. Arrow like that. Okay? Partial what on the O? Yep. Partial plus on the C. Okay? CO2. Helps to be able to actually see this, I think. Okay. Linear, right? Straight out from each other, not bent. Linear, okay? O's pulling that way. That O's pulling that way, okay? Think of this, when we're doing polarity now, we have to think of the whole molecule, okay? We can have these two polar bonds in here, but for polarity, we have to think of the whole molecule, okay? And we have to think of this like a big tug of war happening in this molecule. Like O's pulling that way, that O's pulling that way. I've got a little tug of war right there, okay? They're pulling from this carbon with the same strength, right? Because that's an O and that's an O, okay? This pull is going to be the same as that pull, okay? In opposite directions and straight across from each other, okay? So what do you think would happen if those were two forces? If this was a tug of war, what would the result be? Yeah, it would be equal. It would be a tie, okay? So there's no overall pulling to one direction or another overall, okay? So what we're actually going to say here is that these arrows cancel fully. That's important. Okay. And in order for a molecule to be polar, we have to be able to identify a plus side and a minus side. Okay? Can we identify a plus side and a minus side to this? Is there a way I could divide this to get all the pluses on one side and the minuses on the other side? Not really. Okay? It's pulling equally out. And just looking at this molecule overall, there's not a way for there to be minus on one half and plus on the other half. Okay? So what does that make CO2? Makes CO2 non-polar. Okay? We can have polar covalent bonds okay. We do have polar covalent bonds, right? The CO, okay? But the molecule is non-polar if what about those polar covalent bonds happens? If their forces exactly cancel. Okay? Okay. Okay. So clearly up there, we had a polar molecule because it was just one arrow. That showed how we were pulling. Here we had two arrows, but they were straight across from each other, so they canceled each other out. Okay? Go to your next page, and we'll draw water. What is this shape called? Bent. And it's important that you draw it with that bent shape. If we're ever talking about polarity, the shape of the molecule counts. Okay? And it's that bent shape that actually gives us our answer here. Which a little nicer there. Okay. All right. So we'll have arrows here, but they'll be pointed towards what? They'll be pointed towards O. Okay. That makes O partial negative, H partial positive. Okay. And again, what is it about the drawing that made this bent instead of linear? The dots on the central atom, okay, made this bent. Okay. we've got a pulling towards O that way, pulling towards O that way. Okay? Now, the fact that they're both going towards the middle, that doesn't change anything, because if it was actually linear, if it was like that, okay, and they were both going towards the middle, what would those two forces do? Those would cancel out, okay, if they were straight across from each other. These are not straight across from each other, okay? And that's important. They're the same strength. They're both pointing towards the middle, but they're not straight across from each other, okay? So there is actually a way now, because it's bent, to divide this molecule into a minus side and a plus side. How would we divide it up? What do you think? Yeah, what if we cut it like that? Okay? Simply because it's bent, we're allowed to have this division now, where here is the partial minus side, here is the partial plus side. Okay? So, what direction would the net dipole moment point? The net dipole moment is just one arrow that's sort of the average. If you have multiple arrows in your molecule, it's sort of the average of those. And it defines the plus side of the molecule pointing to the minus side of the molecule. Point with your finger what direction you think that net dipole moment would be. What do you think? I think it would be up. Okay? If you've got this arrow here and that arrow here, again, they would cancel if they were straight across from each other. Okay? But the average of those is going to be an upwards pointing arrow. Okay? Way to think of that. That a northeast arrow plus a northwest arrow is just a north arrow. I don't need parentheses there. Let's make that one red. Okay. See how that works? An east arrow and a west arrow would just totally cancel out. Okay? But northeast and northwest both have north in common. Okay? So, water is what then? Polar or nonpolar? It has a net dipole moment. It can be divided into a minus side and a plus side. Okay? If you can identify a net dipole moment, that automatically makes the molecule polar. Okay? The net dipole moment defines the polarity of a molecule, okay, in other words. And this is kind of a neat picture. Computer programs can calculate where there are more electrons than usual or less electrons than usual, and it can sort of color code it like that. What do you suppose the red color means? Yeah, that means more electrons. And the blue color means kind of less electrons than normal. So we can see the red side, the kind of hot side of that molecule, has extra electrons to it. That makes it the minus side. And the blue side, kind of down near the bottom, is the plus side. So water molecules are polar. That means water molecules sort of stick to each other like magnets, like we talked about. Okay. Alrighty. CH2, Cl2. Carbon makes 4 bonds, right? You got a carbon and then you got 4 atoms to attach to it, so it's a pretty simple structure. But what is that shape called when we have a carbon with 4 bonds? I've got it right here. It's not up, down, left, right. Okay? If you drew something that looks like a plus sign, scribble it out and try again. Okay? The shape is very important. What is this called again? Tetrahedral. Okay? A tetrahedral shape has 4 things going out 3-dimensionally in all directions, and it looks like this. That's how 4 things spread themselves out around a point. Okay? So, and it doesn't matter which one you draw in what place, okay? But draw one of them going up. Where'd my pen go? And then 3 of them going sort of down. Okay? Don't draw any one going straight down either. Okay? You could get yourself into a little trouble if you drew one straight down. So draw this one off to the side a little bit. Okay? It's just a little perspective in the drawing. Okay? So it's sort of like that. Okay? But again, you can draw those 2 chlorines in any of those 2 positions. It doesn't matter. Okay? You name 2 positions, I can put 2 chlorines there. Okay? The 2 kind of right ones, or I could do the left one and the right one, okay? Or the top one and the front one, right? So you can do how you can put those in whatever positions you want. Doesn't matter. Okay? You're going to have arrows. Here, I'm going to do. Like I said, it doesn't matter, but I'm going to do chlorines there. Don't change yours if you put them in different places, and it doesn't matter. Okay? But we're going to do arrows pointing from the what to the what? Carbon to the chlorine. Okay? So even if you had yours up over here or down over here or wherever, point your arrows from the carbon to the chlorine. Okay? Because this is one that's actually easier to see a little bit in the 3-dimensional model. Okay? If I have it like this, I can put my hand right here, and that's the minus side of this molecule. Okay? No matter how you've got it. And I can put my hand over here, and that's the plus side of this molecule. Okay? So again, you can have it drawn either way. It's sort of the most difficult one to see is going up and going towards you. That's a little harder to see on paper, but still in the model, it's exactly the same. If you just looked at mine up here with that arrow and that arrow, point with your finger for me which direction the net dipole moment would go. It would sort of be the average of those 2. What do you think? Got one over that way, one over that way. Point for me. Yeah. I'm thinking something that would sort of go in between those, right? But if you put your chlorines over here, you'd have the net dipole moment that way. Okay? Net dipole moment depends entirely on how you've chosen to draw your molecule. For mine, it is like that, just kind of the average direction there. Okay? But it could have been here if it was those 2, or here. If it was these 2, it would be something like that, kind of bisecting them that way. Okay? So, what do you think? Polar or nonpolar? Yeah. The problem with drawing it with the wrong shape, I'm going to draw it like this and put an X through it. Okay. But if that's the shape you drew, can you see how you might come to the wrong conclusion in that one? What would it look like the arrows would do if that was your structure? It looks like they cancel. Okay? They actually don't. There are no 2 bonds in a tetrahedron that are straight across from each other. Okay? So that's why it's always better to draw a tetrahedron like that. Okay? Or at the very least have it so that no 2 are straight across from each other. Okay? But probably easiest to do making it like a tripod with one pointing up. Okay? But no matter what, 2 arrows will add up to a net dipole moment. If we're doing this 3-dimensionally, the net dipole moment will be sort of in the direction that's right between those 2, like that. See how that works? Okay? Let's take a few minutes. Why don't you guys draw the structures of CF4, NH3, and FCN, and do just what we did. Draw the arrows on the bonds, decide if the arrows cancel out fully, or if they add up to a net dipole moment. if you're ever asked on an assignment or a quiz or something like that, if a molecule is polar or nonpolar, this is what you do. You draw its structure with the correct shape, with the proper perspective, draw the arrows on the bonds, and then figure out if the arrows cancel out or if they add up to something overall. NH3 we've actually already drawn with the arrows even. Now you just have to figure out how they add up. For that last one, make sure you draw the shape correctly. Go back to your list of shapes if you need to. They only cancel if they're equal strength and straight across from each other. Talk about that. The only way that arrows will cancel is if they are symmetrical and equal in strength. Okay? Good. CF4 is tetrahedral, right? The arrows point to the F's. But remember, the whole thing about a tetrahedron is that those are four things that are spread out three-dimensionally around a single point. Okay? So, is that polar or nonpolar? That's nonpolar. Okay? These arrows completely cancel. Why? Because they're symmetrical and what are my two criteria for canceling? Symmetrical and equal strength, let's say. NH3 we drew before, like that. We drew the arrows pointing to the N. Okay. Do those arrows cancel? No, they do not. At least if you drew it in this direction with the dots up on top, what direction would the net dipole moment point? It would point up. You've got a tripod, okay? You've got three arrows pointing into the middle, but they all have an upwards component to them. Okay? So net dipole moment, upwards direction, simply having a net dipole moment makes a molecule polar. We've got a minus side up here, plus side down there. Okay? What shape is FCN? FCN is linear. That's important. No dots on that C. You can draw the dots on the F and the N. Okay? But no dots on that C. There would have to be dots there to make it bent. Okay? So pulling that way, right? What about over here? CNN, yep. Pulling to the right. But the thing is, I'm going to make it a little arrow to the right. Why do you suppose I did that? Which of the F or N, which of those is pulling stronger from the carbon? Yeah. Think of it like a 3-person tug of war with one person in the middle or something like that. Okay? So F and C, they're farther apart from each other than F and C versus F and N. Okay? N is here, C is here. So the difference in strength is greater between F and C. Okay? There's a greater disparity in the it's more unequal in there. So I drew a big arrow over here. I drew a little arrow over here. Those arrows do not cancel. In order to cancel, they have to be symmetrical and equal strength. What direction, on mine at least up here, point with your finger what direction the net dipole moment would be. Yes, this would be overall that way. Okay? I'm going to make it something like that. Okay? They are symmetrical, but not equal strength. FCN is polar. Okay? So, we didn't have time to summarize the different directions and how their arrows work. This will be sort of more of a reference. I'll put this page up completed in the notes that you can download on the website on D2L. Okay? So this just says what those different shapes do if all of them are equal strength versus if any of them are different. Okay? And you'll see the sort of pattern it forms. But this at least gives you what you need to do the assignment and be ready for the quiz on Tuesday. Thank you very much, everybody.